Continuing on with the topic of locomotion, we're looking now at what the bone adaptations that allow this to happen. So in lab, you will see eventually some examples of these bones, and you've already seen the cat skeleton to some extent shows adaptations for cursorial movement, including the lack of a clavicle. But what's really interesting with cursorial mammals and in the ungulates is the loss of bone and fusion of bones, in addition to the lengthening of bones. Remember, a longer bone is heavier, so typically a longer bone is going to be proportionally skinnier. One way to lose some of the weight of a longer bone is to lose some bones, or have two bones fused into one. Not that any of this is intentional or has to happen or is inevitable, just in evolution. You have selection for the loss of bones over time. Think about, this happens a lot. Think about your cat and dog that have dew claws. You know, they just lost their thumbs, big toes. Functionally, at some point that happened. So here we're talking about bones, two bones like the tibia and fibula in some cases becoming fused into one, or a radius and ulna becoming fused into one. And then also these multiple bones in the what we think of as our hand becoming fused are lost. So look at a cow. We don't think of a cow, of course, as being cursorial, or but it is an ungulate. And you do see some of these adaptations. So we have quite a bit of weight perched up here on limbs, so that the weight distributed mostly straight down. So nobody expects cattle, Bolstosaurus, to be really very agile or mobile, but they actually can run pretty fast. What we do see here are these adaptations here. So, for example, if you look at this leg here, you might think that that might be this right here, where number 10 is, or number 20 here, might correspond to the knee. I think average person would just look at this skeleton like, yeah, that must be the knee here, and this must be the elbow, right? So 10 is about where the elbow is, and 20 is about where the knee is, right? Well, no. 20, in fact, over here is corresponds to the heel bone, and 10 corresponds to the wrist. What does that leave? That leaves extended hand and foot bones. So you think of as a broad hand or foot in a plantigrade mammal, and it gets longer and skinnier and extends out to become part of that longer overall limb. So we have a loss of bones and fusions of bones. So what do we have here? Number 12 are these are phalanges. 1, 2, 3, we all have those, but there's only 2 in a bovid. What is number 13? 13 are the sesamoid bones. This is what we have here. I might give you carpal tunnel. If you have carpal tunnel syndrome, it has to do with inflammation, an arthritic type of condition involving those bones. How about 11? What is 11? These are the metacarpal bones, but bones, S, plural, are metacarpal bones. Are these long bones right here? You only have one of those in this ungulate here, the bovids. 10 carpal bones, wrist bones. And then moving on up here, you have an ulna, which is number 9, and 8 is, so you actually do have a separate ulna and radius here. So by the way, ulna, olecranian process, elbow. So you can remember that blade right there. They actually do have 2 bones, functional, and then you have the humerus and scapula. In the back here, very similarly, you have fused bones, bones in some cases. When you get here to 21, you have the metatarsal bones, and this actually go up here to 18. 18 is the tibia, and where is the fibula? It's number 19. Boy, hey, where's, look at number 19 here. Where's the fibula? It's just basically not there. It's effectively gone. It's just a little bump. Bone fusion. Similarly, even in a cat. Actually, this is not comparing to a cat. Yeah, this is a non-ungulate. So this would be more like a human here. You have completely separate, radius and ulna just kind of line up parallel to each other. But if you look back here, look at this, you have a functional fibula. It's not very large, but it still functions. And it's also a brace You don't have fusion of the metatarsals. You don't have, or the metacarpals. You look at a sheep very similarly here, but looks like proportionally, the lower half here, what looks like leg is actually foot and hand. Pretty remarkable. Birds, by the way, the same way. Birds are theropods in the Dinosauria, dinosaurs, and what you're seeing on a bird is mostly foot. That is also an adaptation to running. Birds run, yeah, actually they run really well, but they're adapted from a running dinosaur, the theropods. Horses, this is hard to believe. You see a horse running, that bend right there is the bend in the wrist. Here's the ankle. I think most people say that, call that the knee. Call this the elbow. No, the elbow is up here. So if I'm going to run like an ungulate, I'm going to tuck this arm here. And I mean, they do move their whole limb, but what you're seeing here is all this. Mostly, imagine this. Imagine this is half of your visible limb that's moving. Much of the weight's tucked in here into the center of mass with relatively skinny foot bones, lengthened, fused, sticking out. So here's what we'll have in lab here. We have a horse limbs to look at here. This is the most extreme example of fusion. You have, for example, a cannon bone. What the heck is a cannon bone? Cannon bone is the third metacarpal. So third metacarpal. So that's your thumb is 1, forefinger, middle finger is 3. So horses have a middle finger only. They've lost all the other fingers. And come down here to the metacarpal corresponding to that, it's just 1. They've lost the others. And that 1 has now taken on full duty of all the strength and contributing to that limb, which provides a stride. It's called the cannon bone. And similarly, the digits here, you're down to just these 3 phalanges here, and they are relatively large, strong, and they contribute to this one linear structure here. Moving on up here, notice you have the radius and ulna fused together. There's the cranium process, elbow. And look at the humerus. So our humerus is half of our arm. That is not the case for a horse. It's like a fourth maybe of the arm. And then the scapula. No clavicle. How about the hind limb? Ankle bone. So look at this. Half of the limb is from the ankle down. How about the femur? Our strong, long femur in us. It's half of our lower limb. It's only about a quarter of the horse's limb, and it's tucked up into the center of mass in this bundles of muscle, and you don't see it as a distinct thing. You can't put your hand on it and even feel it. It's surrounded by muscle. What you do see sticking out is this long bone, most of which is foot and ankle. We have a lengthening, strengthening, bone fusion. Here's what's called the split bone, which is the second and fourth metatarsals fused. But you only see one thing, that's called the cannon bone. Notice also you have weight distributed on one structure. Now, horses' legs, of course, are very sensitive. That is, they cannot tolerate a break. Basically, no breaks allowed. They don't do a lot. Now they can, think about polo horses, what they do, maneuvering, front, back, side to side. Horses can do a lot of things, but really they're more adapted to running in the single plane. Look at our limb here, the radius and ulna interacting to provide strength, but also rotation. So a horse, not that a horse is ever going to play piano or do have dexterity. They don't have any dexterity at all. They don't need it. We need dexterity, need all of our fingers. And so we need to be able to have that rotational ability. Horses have no rotational ability at all. If you take a limb, you cannot do this to it. But that's a good thing. And it's actually prohibited. So the way you keep a movement from happening is you prohibit it. So actually the limb can't really, if you're a horse, you couldn't rotate it. And it would be hard to do this. Pretty remarkable, the structure here, as you'll see in lab. I'll bring it out and you can see it. Look at this last phalange. So it's taken on the shape of the hoof. We think of it as the horse's hoof. Well, there's a bone in there that has the same shape. Imagine the last phalange looking like that. And it'll be actually the middle one. What's really great is, and this is something that when Darwin figured out a way of trying to explain how the diversity of life, and it occurred to him like, oh, of course, we all basically share a common ancestor, and which means, of course, someone said, well, wait a minute, yeah, so horses, for example, what was that? There must have been at some point, it must have been a half horse and a quarter horse, like quarter horse, right? A little. So if horses, these ungulates evolved from something that wasn't an ungulate, and we should see the transition to the ungulates. Hey, we do. We have really nice fossils of horses. It's one of the great examples. Whales are another example. We have really good fossils. We don't have it for primates, unfortunately, or bats, but we do have it for horses. What you see is things like Hydrocatherium, which is a primitive horse going back to the early Cenozoic. Yeah, we have little short horses there that had all of their functional metacarpals and metatarsals. And so you can actually see the loss of these bones, the different species, and the transition higher and higher in the fossil record, all the way there. So here's the transition right there. And Darwin, fortunately, had access to some of these, not himself. He didn't really defend himself in public, but others did. And they say, yeah, we already have the fossils. There's the transition right there. There it is. And today, like for example, in pigs, you do see these not extra, but you see that the fusion didn't go all the way. They maintained, and in fact, even deer have they have 4 digits, and sometimes those back 2 will contact the ground. Horses, you see the transition even with the skulls as well, the transition in herbivory. What horses are enormous grass-eating machines. So they've adapted to eating grass out in open areas, and grasses are evolved and really distributed themselves across landscape as an actual ecosystem. Horses filled that niche, and because it's a really unpalatable, pretty much a terrible kind of food. But if you can eat a lot of it and process it continuously and rapidly, then there's a lot of calories in that. You know how much energy there is in grass if you've ever been near a grass fire and felt the energy from that and the heat from that. Grass has a lot of energy, but you have the teeth and the skull to be able to process it, and can you eat enough of it? And if you're living out in large, big open environments, can you run from predators to be able to survive in those environments? That's the horse. And here's the depictions of what they might have looked like. We don't know what color they were, what the flesh really looked like, but fortunately, they did look like this when you articulate the skeletons, and we see the whole transition. It was really nice. There's a nice video on that. Yeah, really great example of transitional forms. And you can, yeah. You see the same thing with whales as well, even in the evolution of teeth. Horses have an enormous skull, enormous lower jaw. They are, now, of course, we feed them, mostly domestic horses, grain and alfalfa, which is not a grass. And so that's unnatural. So horses have to have their teeth actually filed if you have a domestic horse, because they don't eat enough grass to keep them filed down naturally. So this thing about the ungulates, there's traditional groupings were called the odd toed versus even toed. And they do break down taxonomically pretty well for that. The odd toed was the main axis passes through digit number 3. So that includes those that only have a digit number 3, the horses, the Perissodactyla, and it includes those things such as rhinos. where the digit only goes through the third digit, but they have on either side number 2 and 4. So here's an example here. Even though the rhino's hoof is almost elephant-like and it's all enclosed in this one big structure, gravoportal, down in there are 2 other digits there which contribute to balance and to weight distribution. But the main axis of the weight passes through that third digit. They are the odd-toed, 1 or 3. Of course, that means that the others are, and this is Perissodactyla. Here's a tapir, which is the same thing, even though they have 4 digits. The main distribution of weight is through digit number 3. Compare that to the even-toed, which are basically the 2s or 4s. So white-tailed deer have, and cervids and bovids and suids have these 2, and oftentimes 2 behind, which are more like dew claws and don't really have a function. So the weight distribution is passed through digits number 3 and 4, and number 1 and 5 are gone. So imagine losing your thumb and your little finger, or your big toe and your little pinky toe. Sometimes I wish I would lose my little pinky toe, since it's given me so much trouble throughout my life. When we're hiking boots, it oftentimes gets kind of sore. You probably hit your pinky toe and things. I wouldn't be surprised if the pinky toe in humans is going away, evolutionarily, being lost. That's easy to imagine. Losing your big toe, not so easy. When I was a kid, our neighbor, her big toe had to be amputated because it was damaged by a lawnmower. And so she had to sort of change the way, she had to kind of learn how to walk normally again without that big toe. So our big toe does, digit number 1 is important to us. And obviously, digit number 1 is important for humans on the front limb. And finally, the elephant's example, and also rhinos and hippos and some other extinct mammals. I've gone down this line, which many vertebrates have gone down, which is to the large size line, the evolution of large size, and all the positives and negatives that go along with it. If you watch elephants move, much of their weight, of course, all their weight, they're like a typical ungulate. The weight's all distributed in a column, because bone is very strong, that way. Like, you can build a skyscraper as tall as you want, as long as the weight stays down into the materials, the steel and the concrete. But so they're columnar limbs. Think about Gothic cathedrals. And they typically stay under the body. So you're not going to have them walking spraddled like this, and you're not going to have weight distributing out. Another thing about the elephants is they don't have very strong muscles, large muscles, like as large muscles you would think they would have. So look at this thing walking away from me. It's actually the muscles being practically atrophied compared to those of, say, a horse. They don't waste a lot of muscle mass on movements that they don't need to do. If you watch elephants move, how do they move? They move like this. We all pretty familiar. What do they have to do? Now, they can run if they have to, but they don't really need to run. One thing being large is you avoid predators. But they pretty much walk in one plane. Don't swing their legs around much. What do they need to do? They need to eat trees. They are adapted for eating trees and tree bark. And so they are, so look at the weight, heavy weight distributed mostly in the columns. There is bending. They can bend their legs. They do. They have a stride. They can run. But the most of the weight is distributed straight down, although that is bending apparently exaggerated. If you look at the biomechanics of that, apparently they are more flexible than they've been depicted. But if you do look at the limb, leaves no doubt. And you see the same thing in the big herbivorous dinosaurs, the sauropods. Same thing, where you have given up some mobility in return for having a limb that can support a lot of weight straight up and down. Not a lot of bone fusion here, but definitely a columnar limb. So, and then, obviously down here at the base, now, what do you do about toes? Now, you get down to the end, toes are not typically thick and strong as the other upper limbs. You have all this weight, all this strength, all this ability to hold weight, but then what about the limbs? Well, that gets distributed out into tissue. soft tissue. So the elephant's foot is an amazing adaptation in itself. But here's a really nice diagram showing what that actually looks like. It looks like our foot. So actually they're plantigrade. So this looks almost like a human foot here. Imagine walking on high heels, but back there, instead of the sharp little thing where the heel is, it's a big fatty pad. It's all enclosed in a leathery, fleshy, massive connective tissue. Look, they have nails as well. You imagine claws would get in the way. So that you form this sauropod-like foot here. But you don't really see the bones in there. But this looks so much like a sauropod dinosaur, extinct herbivorous dinosaur foot here, the bones do. This was unfortunately, one of the reasons elephants, for ivory, they were almost, African elephants were driven almost to extinction. They're still in danger now. Some populations are, but people used to use the foot actually as a container. It's crazy. They would put umbrellas in them. They would hollow it out and make an umbrella holder for it. It's crazy. But anyway, they use a fatty cushion here, the connective tissue, to take some of that weight and distribute it out. It's pretty neat. And this is probably also considered a source of energy, potential energy for the elephant during the dry season when it doesn't get as much food. I'm sure you tend to draw from your reserves of fat. So that ends this topic of locomotion. Like I said, in lab, we'll have some, you get to be able to get your hands on some of the examples of these.